Hello guys, welcome to the module 2 and part 1 where we will be discussing the topic of transforming the traditional web into web of data. So in the last class we have talked about what is the concept of web of data, right? So let us try to recapitulate a bit what we discussed in the last class. So the challenge that we have faced is with the current web, of course, is that there are information scattered in different places, basically different websites. Now, for a complex task or a complex query that has been put to the internet, the human being himself or herself has to go to different websites, gather relevant information from different websites that are having different styles, different purpose, different languages, and then mentally integrate the information extracted from those pages or documents, and then you get an answer, right? Now, the second question we asked whether we can delegate this mental integration task to machines, right? Now, what was the kind of requirement if we want to implement that? The requirement was that the documents or the pages on the internet, they should be machine understandable on top of being human understandable. The documents, they are human understandable, we know, but we also require these documents to be understood by the machines or the programs, right? And not only that, the second requirement that came up is the way we can link one document to another document using hyperlinks on the internet or www. We should be able to connect a piece of data item with another piece of data item. And if we can do that, we can come up with a very complex structure where an entity will be an entry in this web of data, and this entity would be described by different properties, different attributes, and as we can be able to link these entities together, it will be forming a giant network of information, right? So that was the layer of web of data, right? And we also talked about another layer, which is the sense making layer, right? So there we try to put the concepts, the generic concepts that are relevant for a particular domain, and the relationship between these concepts. And finally, there should be a connection between the web of data layer to the sense making layer. So at the bottom, we have got the human consumption layer. On top of that, we have got the uh, mm, web of data layer, and on top of that, we have got the sense making layer, right? So from this, let us start talking about, if we have the web as we see today, uh, how or what strategy or what benefit we will get if we transform the web into web of data, right? Now let us first look at what are the issues with the current web. Now while we are trying to access data, the data basically at this point of time, we can think of their documents. The data is put or embedded into a set of documents that are there on the internet. And the search engines, they can index the documents, and the indexing is done mostly by help of analyzing the text. So basically you can think of index to be which document talks about which word, right? Now, if you put a query in the search engine, the query text will be matched against the indexed words, against the indexed documents, of course. And then, whenever you find a match with a set of words and the queries, the documents that are aligned to these words in the index will be returned as your results, right? Now, there is an issue on this if we talk about the ambiguous queries, the queries that have multiple meanings. So, let us take a query like that, right? So, such a query is Watson. So let's say someone is searching for Watson. Now Watson can mean many things, right, or many entities, right? So first entity that might come up in mind is the Dr. Watson, the assistant of Sherlock Holmes, right? Sherlock Holmes stories. The second one can be Emma Watson, who played or acted in Harry Potter movies, right? The third entity can be James D. Watson, who was instrumental in proposing the double helix model of DNA along with Crick. And Watson can be a computer program, AI-enabled computer program by IBM, and that is called IBM Watson, right? Now, you can see that there are multiple options or multiple entities that can be a possible answer. So what would be the answer in this case, right? So this is the problem. The second problem is that if you have a complex query and that involves a bit of inference. It is not a very straightforward, like who invented, say, time machine. I don't know if you have any answer, but let's say who invented, say, semantic web, right? So these queries are straightforward. So these are factual queries and they are more or less pretty straightforward to answer, and the search engines, they do well in answering these queries. But if some query has certain elements that requires inference to be made, for example, this is the query that I'll ask to the search engine, like where can I go on holiday next week for 3 days with two young children for less than 1 lakh rupees in total. You can see that it's a very complex requirement, and there are lots of inference involved in order to provide a correct or good answer or satisfying answer to this query. And you know that these queries are not satisfiable by the current web. Now, if we look at web, so they are basically or the search on the web. The search on the web is basically you are best fitting the query to the documents. So that would be a very simplistic way to say the search on the web, right? Now, the search engines, they do well in matching the queries with the documents, but they fail to integrate information from multiple sources to answer a query, right? Though the search engines, they are getting better day by day. So for example, if you look at search in Google or Bing or any other search engines, for a given search query, you can get multimodal results. Like you can get links to the text document, you can get images as results, you can get videos as result, but they do not integrate the information or content inside the documents and putting together or integrating the information and presenting a very crystallized answer to the user for a given query. And the integration, needless to say, is left to the users, right? Now there is something called the dark web. So the dark web is basically, there are plenty of data available over the internet, but they are hidden from the user. Think about a web application where there are many books, for example, and in order to access those books, you have to log into the system or log into the application. So in that case, you can see the login page, though is accessible to the search engines, the pages that are hidden under the login wall, they will not be accessible by the search engines to index, right? And basically this is the case of the pages which are dynamic. You put some input to the system or application, the application goes to the database and come up with an answer and present it to the user, right? So you can think of booking a flight from one place to another place, or booking a hotel. So what you are doing, you are specifying your intent that this is the thing and this is the exact requirement and you are getting some answer, but you get a very small fragment of the entire data set they are having with them, right? So we can see something, but they are much beyond it, and as they are hidden, so that's why that part of the web is called dark web. So though they are uh, on the web, they are not discoverable, right? Now, there are certain ways by which you can resolve these issues, like you can write a web scraper to get the documents or the contents of the documents. But again, web scrapers, they are error prone. If you uh, have some problems in the document, your program can fail. And it is unstable in the sense, if the content provider changes the document a bit, your scraper might not work, right? So the web, in short, is really huge or really big. So by the estimate of 2017, the number of index documents by the search engines put together is around 47 multiplied 10 to the power 9. You can see the scale, but there are much more hidden under it. So there are around 550 times more contents that are there on the web, and they are the part of the dark web or hidden web, right? And of course, this content repository is growing larger day by day by the posts in different forums, in different blogs, different social media platforms, right? Now, at this point, computers, they are only rendering devices. They do not have any inferential capability as far as the contents in the web they are concerned. So we need to make it more smarter so that they can analyze the data and make sense out of the contents that are there on the internet. Now, the question is, how do we make web intelligent? And the simple answer to that is you add meaning to the web. So the documents we can see on today's web, they are passive. They are the meaning of them, these documents, they are not explicit. As they are not explicit, only human being can go read, and if the person is in that domain of the content, he or she can understand the document. He or she can understand the meaning or semantics of the content. Now the solution to this question or solution to this problem is you add meaning, add semantics to the web. I think the entire course will be dealing with the ideas around this solution. Now, when we talk about meaning, what is the meaning of meaning, right? So for that, we'll take help of this triangle. Right? So in this triangle, we have got three things. One is the concept, the representation, and the referent. Now, when meaning gets importance, when we try to convey some idea or concept to the receiver. So a sender is trying to send a message to the receiver with an intention that the receiver will understand the idea. And how do we represent our ideas mentally? Basically, the ideas are represented by a set of concepts. So for example, if we think about this online uh, education, online teaching, and you want to convey something on this online teaching. So for example, the goods and bads of online teaching. So there you can be having different concepts, like online teaching is itself a concept. The teaching, the learning platforms, there are some concepts, right? So basically you have a mental representation of the real world thing. And what are the real world things are there here? So for example, you have got this jaguar to be the real world thing, the animal jaguar, the car jaguar, or jaguar related to Mac OS, right? So they are the real world thing. And while we are trying to represent them mentally, we represent them as concepts. And these concepts, they refer to this referent, which are the real world things, right? Now these concepts, while we try to communicate to the receivers, we symbolize the concept. So symbol in this case is the Jaguar word, which is basically a sequence of letters, or it can be a speech signals or speech utterance, right? Or it can be a picture as well, right? So we are symbolizing the concept using either a sign or a term or a symbol, and we use those symbols to convey the concept or idea from the sender to the receiver, right? So that's why we say the representation symbolizes the concept. The concept refers to the referent, and by doing this like the way I mentioned, that representation symbolizes concept and concept refers to referent, this representation finally stands for the referent. So whenever we say jaguar in the animal sense, then we have the picture of the animal jaguar coming into our mind, right? And basically this conceptualization is the representation of meaning of meaning of an entity, right? Or real world thing, right? And you can think this to be a very philosophical concept, which is called the semiotic triangle, but we'll see that we'll be having a very practical representation of this while we are trying to uh, mm, model the meanings of the different things on the web, right? So semantics is there in computer science from the very beginning, but in different ways. So the most simplest way to embed semantics is to embed them directly in the programming language, right? So whenever we write a program, we make use of different data structures. They can be simple, they can be complex. If you take the example of an array, so the array, what does it store? It stores a number of elements. It can be an integer, it can be a floating point number, it can be a string also, right? Now the meaning of the elements or the semantics of the elements in this array will depend on how you are manipulating the array in the program. So if they represent, say, marks of the students in different exams, then you will treat the array differently than if it represents the score of a particular cricketer for, say, last 10 innings, right? So the point is, the meaning of the data or the semantics of the data is completely hardwired into program, right? And if we have that kind of setting, what is the problem? The problem is, even though you have a data, you cannot reuse that data in other program. And that's where the database technology came into picture, where we can separate the data from the application, right? And if we do that, we can reuse the same data in different programs, right? And there are different data models that came up and different database technology that came up. They in some way represent the meaning of the data or the semantics of the data. And finally, the natural language documents, they have been gradually been put into the computing systems or specifically over the internet. And the techniques like information retrieval, information extraction, and natural language processing techniques, they came into play to understand the documents or understand the meaning of the documents, text documents, right? There is another aspect of semantics when we come to artificial intelligence. So if you think of artificial intelligence when it started, it has a very ambitious goal of having a generic program that can solve any problem. So those are called generic problem solvers, right? So for example, you have a theorem in geometry which you need to prove. What you are given with? You are given with a set of axioms that are known to be true, and in the geometric domain, you know there are certain rules that are true, or that are some formula that are true, and from these two you have to prove certain goal, right? And this geometry problem can be anything, but your theorem prover, the same theorem prover, the same program should work for any given geometry problem. There are search algorithms which helps in solving a certain problem starting from an initial state. So for example, think about a puzzle. I hope many of you have played this puzzle. In a chessboard, you are given with 8 queens, right? And you have to place the queens in every row and every column so that they do not attack each other. And the definition of attacking is they should not be two queens, they should not be in a same row or same column or same diagonal, right? So your initial state that is given with you is the empty chessboard and 8 queens. And what are the constraints? That you cannot really put two queens on a single row, single column or diagonally, right? And what is your end goal or what you want to achieve? You want to achieve a state where the queens are placed in every row and every column without attacking each other, right? So you can apply many operations, do trial and error process, and maybe you can end up with a solution. But AI algorithms, they have tried to think what could be a very methodological way to solve this problem. And that required a very intelligent method to process world knowledge. So for these 18 problems, the world knowledge is the chessboard and the operations that you can do. So you have to have mechanism to represent this knowledge and process this knowledge. And this knowledge should be machine understandable so that the programs, they can manipulate the data and infer something about the data. And these kind of requirements, they spawn certain areas like knowledge representation and knowledge engineering. Basically, these are the two core elements. If we talk about talk in a theoretical sense, are two very important aspect of this course. And this has been nicely done using computational logic, right? And in our course, there will be a significant portion of how do we implement the ideas of semantic web using different logics. And what is the relation between semantics and the web? So basically, this is what we are trying to stress upon from the first class, that the web of data or web of knowledge is really an upgrade of the web of documents. So we are trying to make web of documents to be smarter, right, by injecting structured data into the web. And if we do so, you can think this web to be a huge decentralized database. So you can just think of a scenario where each document has a structured data about the content, and you can connect a piece of data item in a document to another piece of data item in another document. So you can see that you are connecting different dots and they are becoming to be a giant database which you can query and get answer from. And of course, as they are put in a structured form, they are machine processable or they are accessible by machines. And this is what Sir Tim Berners-Lee talked about while we are talking about implementing the web of data on the current web. So here it goes. The web of human readable document is being merged with a web of machine understandable data. The potential of mixture of humans and machines working together and communication through the web could be immense, right? So this is what we are trying to stress upon from the first class, that whenever we are creating structured data about the contents, basically we are trying to establish communication between human and machine. So what do we mean by WWW2 web of data? Basically, this is the crux of the entire problem. How could we make machines read and understand web of contents, right? So this is the basic objective. Now, this objective can be achieved in two broad ways, and both the ways have their own merit and demerit. So the first way is the way of natural language processing. So you have the unstructured text over the internet. You employ natural language processing techniques, information retrieval techniques, and infer meaning out of the content. And this is quite successful. If you think about the search engines, they are following some form of this approach, right? And nowadays you have question answering in the search engine itself, right? And they are using some form of natural language processing. The other way is the semantic web way of achieving this objective, right? And what does it say? It says that you explicitly mention the semantic structure of the content manually. You make it explicit. You don't assume that the computers will be employing a natural language processing technique to understand. You assume that they are a bit dumb, and you want to embed the semantics of the content itself in the document. And this is exactly what is called a semantic metadata. Metadata is basically a description, a structured description of an entity. You can think of a book. A book has a title, book has a number of pages, book has one or more author, book has a publisher. So all these little piece of information they put together is the metadata of that book. So you can think of a web document like that. It is having many things. It has got many statements that it believes to be true, many statements it believes to be false, and there are many important description about different entities. So if you can explicitly mention them, then the program would be finding it easier to understand the document, right? So we want to have a explicit mention of the structured data in the content itself. So we in this course we will be following this semantic web way of making web smarter. Now, to illustrate whatever we have talked about till now, let us take an example. So this is an excerpt picked up from web blog. It says something like this: Watson does a remarkable job of understanding a tricky question and finding the best answer. Now, what the machine or the program needs to do is to understand which exact real entity Watson refers to. Now, the problem seems to be, I guess, harder because there are many Watsons out there. So that's where the problem is, right? So we have seen an example in the first slide itself, right? So given this context, we have to find out a way, right? Now, given this text, let us try to emulate what the programs might want to do. So first, it can enumerate all the entities that are having relation to this word Watson, right? So you can think of it to be referring to Emma Watson, You can think of it to be referring to IBM Watson. It can be a Dr. Watson, which is a debugger program, not the Dr. Watson of Sherlock Holmes. And also it can be there, the Dr. Watson of the Sherlock Holmes. And maybe Mary Jane Watson, who is a character in Spider-Man movies and stories, right? So the central question is, what is the most appropriate entity? That is something that has to be resolved by the program. And this problem is called notoriously the disambiguation problem, right? Now, we talked about two different ways. So one way is the natural language processing way. So what this natural language processing way we do, they will look at what are the other words in the context of Watson, and they will try to make an inference if we have questions and answers. Maybe Emma Watson will not be a possibility, but Dr. Watson of Sherlock Holmes, because he answers to many questions posed by Sherlock Holmes, or the IBM Watson, which is a question answering system. So it will look into the words that are appearing in the context of Watson and then try to make some inference, right? But the other way is different, where we are explicitly mentioning what this Watson actually refers to, and then what are the other related entities of Watson in this context. So this excerpt, in this excerpt, Watson refers to the IBM Watson, which is a question answering system which defeated the Jeopardy champion, and that was a kind of huge news and breakthrough by IBM. So the meaning of the entities and the classes, they must be defined explicitly. So that is the semantic way of resolving this or addressing this problem. So this Watson refers to IBM Watson, which is an entity. Now entities, they would be mostly the proper nouns, the real things, like an institution like IIT Kharagpur, a person like say Tim Berners-Lee, a machine like IBM Watson, like that. And there can be a relation between the entity and a class, and the class here concerning class here is the question answering agent. So it is a class, and what you are saying that this entity IBM Watson is a class, right? So that means it is an instance of this class. Now mathematically you can represent the class, a class, as a set, and in this case this question answering agent, which is a class, can be represented as the set of all the question answering agents, right? And on top of that you can define certain generic relationships, like question answering agent is subclass of computer program, right? So this does not really depend on whether we are processing this piece of text or other piece of text. This will be true for any document, right? Now we have a structure. So the structure is, we are mapping IBM Watson into an entity. We are mapping the question answering agent to a class. We are mapping computer program to a class, and we have a relationship between the entity to class, like entity has class, and class is a subclass of another class, right? They share a subclass superclass relationship. So while we are trying to represent the knowledge about a domain, so this is exactly what we need to do. We need to specify explicitly what are the templates, what are the concepts that are available in this domain, and what are the kind of relationships that are holding between these concepts. And when we have the concepts, if we have any entity, we will be able to map those entities to different concepts. And this is exactly what is called a knowledge representation schema or ontology. So this particular way of templatizing the knowledge is called the knowledge representation schema or ontology, right? And in this structure, you can see two different parts. One is the abstract schema, other is the domain schema. Now this abstract schema, it applies to any domain. A class can be a subclass of another class. It doesn't really depend on a domain, but whether a question answering agent can be a subclass of the computer program that is applicable to the domain of computer science but may not be relevant or applicable to the other domains, right? Now, with this, we have an expectation that we can infer new knowledge using an existing knowledge representation schema. That's why we are explicitly doing all these things. So, let us see an example of this kind of inference we are talking about. So, let's say we have got multiple classes like question answering system of IBM, question answering system of Google, question answering system of Apple. So they are different classes, right? Now this IBM Watson is a question answering system of IBM. So this is an instance. IBM Watson is an instance. It is an instance and it is belonging to the class of question answering system of IBM, right? And then you define all these classes to be subclasses of question answering agent. Now, if you do so, you can easily infer as human being that IBM Watson is a question answering agent, right? Now, you present another explicit piece of knowledge, that is question answering agent is a subclass of computer program. And from this, we can further infer that IBM Watson is a computer program. And this can be achieved through logical inference, right? We can do more, right? So, not only that you have concepts in the domain schema or knowledge representation schema or ontologies, you can have or you have relations. Concepts without relations have no meaning. So, for example, the question answering agent is related to organization via developed by relation, right? So, whenever we say that a program is being developed by an organization, we represent that with this kind of relation. So, in this case, it is a binary relation. So, a relation that takes two arguments, A and B, right? And we are saying that for this developed by relation, A is an instance or entity that should belong to the concept question answering agent, right? And B should belong to the class organization. So, a specific example of this is, say, developed by this is a relation, and the first entry in this relation is IBM Watson, and the second entry is IBM, say IBM Research. So, what we are doing here, we are basically restricting the set from which this A can belong to and set from which this B can belong to. This A only can belong to the QA agent and B can only belong to organization, right? Here we are imposing the restriction, and these restrictions are called domain restriction if we are imposing the restriction over the first argument, and we are whenever we impose the restriction over the second argument, that is called the range restriction. Again, we will be talking about these in more detail in subsequent lectures. Now we have talked about different structures, etc., etc. Let us take if we do so, the question is, if we do so, what gain or what benefit we'll have, right? To illustrate that, let us take another example, right? So the example is a very complex query which says works of Indian about European colonization of Southeast Asia, right? And let's say you have a document in your repository or in the web. So this is your document D, which has got this statement, right? Now the question is whether I can retrieve this document as an answer to this query, assuming that it has been authored by someone. But is it a candidate? But if you look at this part, European colonization of Southeast Asia, with a human inspection, we can really say that this has got something to do with this document, right? But if we look at the words, the way the search engines work, the Dutch word is not appearing anywhere, though we know that this Dutch is a part of European. Colonization is there is a bit of alignment, but again, Indonesia has got no entry here, right? So the point that I'm trying to make, the traditional search engines, those who are just looking at the keyword-based match, they will be failing to retrieve this document as an answer to this query. Now let us see if we use the concept of semantic web, where we have got the explicit metadata about the documents, whether this query can be answered, right? So there is a think about the real ideal scenario where you have got the huge giant network of web of data, and there somehow you could find this person, Sanjeev Sanyal, who is a type of author and who has the nationality to be Indian, right? So you found the answer to this part, Indian, right? And then this person has authored a book which is called Ocean of Churn, right? And what does this book contains? It contains a statement, and this statement says that the Dutch colonized Indonesia, right? And on top of that, we using some other data, we can know that this Dutch is a part of Europe and Indonesia is a part of Southeast Asia. Now we can see that we have more or less answered this from this part to this part, right? And on top of that, this book is of type non-fiction. And whenever we have a non-fiction, it is also a creative work. Like novel and articles, they are also creative work, right? And we get the answer to these patterns, right? Now you can see that we have traversed the web of data from starting from this place, and we have got the answer to this query, a very crisp and clear answer, which is ocean of churn, right? So this the structure that has been used to answer this query has got two distinct parts. One is the ontology, which is basically the concepts and their relationships, and the other part is the metadata about the entities, the metadata about this book, the metadata about this person, right? And if we merge them together, if we use them together, they form something called knowledge graph. And this knowledge graph has becoming to be a very useful resource by any search engine you can think of in today's world. So I'll give you give you examples of the usage of these knowledge graphs by search engines. Right. Now let us stop here at this point of time. The next video will start working on to see the relationship between semantics and web, but we look at different views, the different ways to look at the relationship between the semantics and the web. Thank you.